Welcome to your first video for Calc 3. I'm going to try to keep this to 15 minutes or less, but trying to condense Calc 3 into 15 minutes can sometimes be a challenge. So we're going to see how it goes. All right, so we're starting with Lesson 1, Algebraic Understanding of Vectors in the Plane. Okay, that's a lot of words. I want to make sure you understand why each of them are there. Algebraic understanding. We're going to start with looking at the numbers and the notation for vectors. And this says vectors. Okay, what the heck is that? A vector is, for all intents and purposes, an arrow. It is a direction with both length and magnitude, direction and magnitude, I should say. And in the plane means we're working with 2D right now, okay? So also with vectors, if you remember Despicable Me, remember there was Vector in Despicable Me, and he says, I commit crimes with both direction and magnitude. That's what we're talking about. So a basic introduction to vectors here. Let me get a pen going. A vector in the plane is basically a 2D arrow or a directed line segment connecting 2 points, the initial point and the terminal point, meaning the start and the end. Draw an arrow starting at A and ending at B. That would be the vector AB. Bloop. There's vector AB. Ta-da, easy peasy. AB can be written in component form, and that's got little pointy brackets, V1, V2, where V1 is your horizontal component. Positive means to the right, negative means to the left. And V2 is your vertical component. Positive means up, negative means down. So if I wanted to write AB in component form, I am going to the right 1, 2, 3, 4, 5, and I am going up 1, 2, 3. So this would be 5, 3. If instead I wanted to write vector BA, that would mean I'm going in the other direction. So I would be going like this, and then I would be going left 5 and down 3. Okay? So AB is a certain vector. BA is the negation of both components of that vector. You negate the vector. All right. So it says the coordinates of A are 2, 3, and B is 7, 6. What do you do with the coordinates to get the component form? Well, the first thing I want you to understand is vector definitions, vector components have nothing to do with where the vector actually is. That vector could be moved anywhere else I want it to go. Let's see if I can actually grab it here. So if I were to grab this vector and move it, okay, it's still got the same notation. It's still going to be 5, 3, and negative 5, negative 3. It does not change where it is. But where it starts and ends, that's how you get the components of the vector. Let's see, undo, sweet. So if I look at 2, 3, and 7, 6, how do I get the components from the points? Well, you literally just subtract. So we did 7 minus 2, comma 6 minus 3. What we really get for a vector is delta x, comma delta y from the initial point to the terminal point. Okay? And if you really want one more, that's x2 minus x1, y2 minus y1. Easy peasy. The magnitude is really the length of the vector. It's the distance between the initial point and the terminal point. The notation for magnitude is either this with double bars around it, or you may see it with single bars around it. And you may be thinking, wait, single bars mean absolute value. Ha, I say, but absolute value has meant magnitude your whole life anyways. What? If you take the absolute value of negative 7, you're really asking how far is it from 0 to negative 7? Absolute value is a magnitude, which is why we allow both notations, because they both work. So if you want the magnitude of the vector, you'll see the vector's name in single bars or double bars means the same thing. If you want to find the magnitude, you could use the distance formula with the coordinates, because magnitude is the distance between the points. But when we look at that, I have the square root of x2 minus x1 squared plus y2 minus y1 squared, and hold on a second, x2 minus x1 and y2 minus y1 really create the components of the vector. So if you have your vector in component form, use the component form to find the magnitude. So if I want to find the magnitude of AB, which we currently have, whoops, I didn't mean to draw that bracket yet, that would be the magnitude of 5, 3, which means I'm just going to square root the sum of the squares of 5 and 3. And 25 plus 9 is 34. There's the magnitude. Okay, so down here it says 2 points have coordinates of -3, 5 and 9, -6. Write PQ and QP in component form. If QR is 2, 5, find the coordinates of point R and find the magnitude of PQ and the magnitude of QR. If you think you can do that on your own, pause this for a second and then scrub to the end to where I answer it. If you think you need help, you can watch me go through it, which I'm going to do right now in purple. All right, so if I want PQ, -3 up to 9 is an increase of 12. So PQ is 12, 5 to -6 is a decrease of 11. So PQ is 12, -11. QP is just the negation of that. So QP is equal to the negation of PQ, which is going to be -12, +11. It says QR is 2, 5. So what does that mean? That means to get from point Q to point R, I have to go 2 in the X direction and 5 in the Y direction. In other words, go 2 to the right and 5 up. So if I started at 9, -6, and I go 2 to the right, I am now at 11. And if I started at -6 and go up 5, I am now at -1. Cool. And then it says find the magnitude of PQ and QR. So the magnitude of PQ is going to be the square root of the sum of the squares of the components. Notice I didn't even write the negative in there because it doesn't matter. So I've got the square root of 144 plus 121 is 265. And then if I want the magnitude of QR, those components were 2 and 5. So I have 25 plus 4, which is 29. There. That part was easy. What do we got next? Special vectors. Okay, so special vectors. The 0 vector. Okay, it's exactly what it sounds like. A 0 vector is a vector with no direction and no length. Really what it means is it's a vector, but all the components of the vector are 0. So a 0 vector is really just a point. Okay, but if I call it a 0 vector, I don't know where it is because every singular point is also the 0 vector. It becomes really important in later things. We'll get there. But a 0 vector is 0, 0. It's often noted by a bold 0 or with a 0 with a line over the top of it, arrow, pardon me, over the top of it. A unit vector, we're going to use those a lot. That's any vector whose magnitude is 1. Standard unit vectors. There are also standard unit vectors. Okay, so any vector with a length of 1 is called a unit vector. And your standard unit vectors are vectors I and j. Once we get into 3D, we're also going to add a k to that. But the I standard unit vector is the vector 1, 0. And the j standard unit vector is the vector 0, 1, where I is a horizontal unit vector and j is a vertical unit vector. We use I and j interchangeably to create other notations for vectors. So there's component form with the brackets, and there's also what I will call standard unit vector form, but that's a mouthful, so I often just say IJK form. There's another form for a vector. The vector 3, -4 can be written as 3i minus 4j. Go 3 in the I direction, go -4 in the j direction. There are benefits to both forms, which you will see later. So this says 2 points are j and k. Write jk in component form and in ij form. All right, well, if I want to get from j to k, jk the vector, x goes down 7, y goes down 5, so jk would be -7, -5. If I want to write that in ij form, I would say -7i minus 5j. And if you're wondering, Mrs. Viver, what are those hats doing? It's because technically the I and the j need to be bold, but because writing bold in pencil is somewhat difficult, you can write the I with a hat on it and the j with a hat on it, and that means the same thing. When I was in college, if you're interested, I used to write these actually bold because that's what my professor did, and I literally make like a block letter, and do it that way. You may see me go either way. It depends on the day because my hand is used to doing both at this point. Okay, operations on vectors. Technically, we just did one, and I'll explain that in a minute. So you can add and subtract vectors algebraically quite easily because you literally add and subtract their components. So if I have 3 points A, B, and C, find the sum of vector AB plus vector AC in component form. All right, well, if I'm going to add AB and AC, I should probably find AB and AC. So AB, the vector, is going to go 1, comma, -7, because from A to B, x goes up 1, y goes down 7. And AC goes from 3, 2 to 9, -6. So x goes up 6, y goes down 8. And now if I want to add AB plus AC, I am literally just going to add those components. 1 plus 6 is 7. -7 plus -8, is -15. That's it. Then it says find the difference AB minus AC. Okay, I just subtract instead. So if I want to do AB minus AC, I'm going to subtract the components. So 1 take away 6 is -5. -7 minus -8 is 1. There it is in component form. Multiplying or dividing vectors. You can't. Don't try. Short answer. I'm kind of lying, but we'll get to that later. But technically speaking, you cannot multiply a vector times another vector using the original multiplication rule or divide. Now, what you can do is you can multiply or divide a vector by a scalar. So you can take a component form of a vector and divide by a singular number, a scalar, and do stuff with that. You just multiply or divide both components by the scalar. So it says using the points above, find the vector 4 times AB. Okay, fine. So if I want 4AB, that means I'm multiplying 4 by 1, -7. And that's going to be 4, -28. That's it. Now, I had said earlier that technically we had already done operations on vectors. We did, because way up here, where we said 3i minus 4j, that's technically 2 scalar multiples of I and j. So if we think about that, I'll do this off to the side, hypothetically, off to the side. There we go. 3i minus 4j really means 3 times 1, 0, minus 4. My lights turned off in my classroom. Hello, I'm in here. Nope, not working. Minus 4 times 0, 1. So that's going to be 3, 0, minus 0, 4. And then when I subtract those components, I get 3, -4. Okay? So when you use IJ form, you're technically doing operations on vectors. Okay? So we did multiplying, dividing vectors. Nope. Multiplying or dividing a vector by a scalar. Yes. Length of a scalar multiple. So what this is getting at is if you multiply a vector by a scalar, it just multiplies the length by that scalar, which is just about as common sense as it sounds. If I take a vector that has a certain magnitude and I multiply that vector by 5, the magnitude gets multiplied by 5. I mean, that's really it. So this says, show that 4AB then magnituded is the same as 4 times the magnitude of AB. Okay, fine. So if I want to show that the magnitude of 4, -28 is equal to the magnitude of, is equal to 4 times the magnitude of 1, -7, let's see, this is going to be the square root of 4 squared plus 28 squared. And I want to show that this is 4 times 1 squared plus 7 squared. Let's see, this one, 7 squared is 49, plus 1 is 50, so this is 4 radical 50, which really ends up being what? I can pull a 25 out, so 20 root 2. And then over here, 4 squared is 16. 28 squared, I am not going to mess with doing that wrong here, so let's make sure I get it right. 28 squared is 784. Look at that. That's going to be the square root of 800. So that's really, let's see, 400 times 2, and the square root of 400 is 20. 20 root 2 here, 20 root 2 there. You never have to prove that again. Just know that if you multiply a vector by a scalar, its magnitude gets multiplied by the same scalar. All right. Creating a unit vector. Fine. How do I make a unit vector? Well, here's the thing. Anybody can make a unit vector. 1, 0, 0, 1, 0, negative 1. There are others. If I want to make a unit vector with a specific direction, that's what we're really getting at here. So it says in order to create a unit vector in the same direction of another vector, you divide the vector by its own magnitude. This is called normalizing a vector, okay? So it says find a vector in the same direction as AC that's 1 unit long. Let's see, what was AC? AC was 6, negative 8. So AC is 6, negative 8. If I want to find a unit vector in the same direction as AC, I'm going to call that U, and I'm going to take AC, and I'm going to divide AC by its own magnitude. Dividing a vector by a magnitude is dividing a vector by a scalar. A vector divided by a scalar is still a vector. It's just going to be a vector with a different magnitude. So I'm going to take 6, negative 8, and I'm going to divide it by the square root of 6 squared plus 8 squared, which is 100. So 6, negative 8 divided by the square root of 100, which is 10, is going to get me the vector 0.6, comma, negative 0.8. That is now a unit vector in the same direction of 6, 8. So what does that really look like? It means if I have a vector 6, 8, and remember, it can be anywhere. So let's say I'm going to go over 6, up 8. Let's say it's this. Here's the vector 6, 8. The vector 0.6, 0.8. Oh, I forgot my negative. Poop. Let me fix it. That was 6, negative 8. Apologies. So to the right 6, down 8, that would put me down here. Whoop. If I want to make that 0.6, comma, negative 0.8, it would just be this itty bitty piece right here that is 1/10 as long as the whole thing. All right, creating a vector of any length in a given direction. So let's say I know what direction I want to go, but I need to go 10 units in that direction. Well, the easiest way to do that is to create a vector that goes 1 unit in that direction and then multiply it by the magnitude you want it to have. So if I want to go a specific direction and a specific length, you're going to take your original direction, divide it by its magnitude to shrink it down, and then stretch it as many times as you need to. So it says find a vector in the same direction of BC that's 5 units long. I don't think I know what BC is right now. So I'm going to scroll back up here. BC from way up here is 5, negative 1. Okay. So if BC is 5, negative 1, and I want a vector in the same direction of that that's 5 units long, what I'm going to do is I'm going to take BC, divide it by its magnitude, and then I'm going to multiply it by 5. That's it, because I shrink it down to a magnitude of 1, multiply that by 5, I now have a magnitude of 5. So that's going to be, let's see, 5 times vector BC, which is 5, negative 1, divided by the magnitude of BC, which is 5 squared plus 1 squared. So that's going to really be 5 divided by the square root of 26, all multiplied by 5, negative 1. And you can leave it like that. You can leave vectors in their nice, happy integer component form and then pull the multiplier out in front. It makes life a lot easier. Okay? All right, and creating a vector of a given length using angles is our last thing. Whoops, I went too far. So it says if I want to make a vector of a given length using angles, we haven't talked about angles at all. Since a vector has both the direction and magnitude, I can indicate direction by horizontal and vertical components, or I can indicate direction using angles, all right? So this says find the component form of a vector whose initial point is the origin, okay, right here, that has a magnitude of 8 and a 30-degree angle with the positive x-axis. So we're saying this is 30, and that's 8 units long. Well, if I want component form, hello trigonometry, there's my horizontal component. There's my horizontal component. I meant vertical for the other one. So I've got my vertical component. There's my horizontal component. I'm just going to use trig. So this is really, let's see, x is the horizontal. It's adjacent to the 30. So katoa, that's going to be cosine. So this is really going to be 8 cos 30, 8 sine 30. And let's see, the cosine of 30 is radical 3 over 2. So 8 root 3 over 2 is 4 root 3. 8 sine 30 is 8 times a half, which is 4. And there it is. All right, I didn't want this video to get too long, so I am going to stop here. The problem is you guys have all heard my jokes before, so I'm going to rehash an old one, and then I promise I'll get some new ones later. So rehashing an old one, what's orange and sounds like a parrot? A carrot. Because carrot sounds like parrot. Okay, I'll stop. Have a great day.